A 100-gram apple? A 1 Newton weight. Now put it in a vacuum. What's its mass? Welcome to the Explainer. Today we're cracking the Cambridge IGCSE Physics 0625 mark scheme wide open using a true data detective approach. We're not just memorizing facts here, we're hunting down the hidden patterns examiners use to test you.
Let's jump right back to that opening problem. A 100-gram apple weighs 1 Newton. What is its mass in a vacuum? Spot the trap yet? Listen, if your instinct was to somehow change the mass because the environment suddenly shifted to a vacuum, well, you've just fallen into literally the most painful dropped mark trap in all of physics.
This exact mistake, mixing up mass and weight, or totally forgetting their specific units, is a massive grade boundary risk. And here's the real issue, right? Ordinary, run-of-the-mill revision completely fails to fix it. Just reading a textbook doesn't wire your brain to spot the examiner's tricks under pressure. So when students see words like vacuum or space on the exam paper, they panic. They start altering constants that should absolutely never be touched.
The high mark framework.
Let's see how this builds into an unbreakable strategy. To write a genuinely top-band answer, you have to run every single question through this 4-step framework. First up, identify the underlying concept. Second, pull the hard evidence or data right from the question. Third, apply your scientific reasoning. And finally, this is crucial, lock it in with precise examiner wording. Look, if you skip step 4, you're doing all the heavy lifting, but leaving the actual points on the table.
Unlocking mass and weight.
Time for our first quick win. Let's apply this framework right now. Mass is a scalar quantity. It's a constant everywhere in the universe, and we strictly measure it in kilograms. Weight, on the other hand, is a vector. It has a specific direction, pulling straight down. It's measured in newtons, and crucially, it actually varies depending on exactly where you are standing.
But why does it vary? Well, the Earth isn't a perfect sphere, right? It's actually a bit squashed, flatter at the poles. Because of that, an object is physically closer to the center of the Earth when it's at the North or South Pole than when it's sitting on the equator. Closer to the center means the Earth attracts it more. So your weight literally changes depending on your latitude, even though the actual atoms making up your body haven't changed one bit. To really prove that mass is a constant everywhere, let's take a quick trip to the moon. The force of gravity up there is just 1/6 of what we feel on Earth. So think about a 12-kilogram mass. It weighs about 120 newtons here on Earth, but a mere 20 newtons on the moon. But here's the absolute kicker. Its mass remains exactly 12 kilograms. Mass is just the amount of matter. It totally doesn't care if it's sitting on Earth, bouncing on the moon, or just floating out in the vacuum of deep space.
Now, in a moment, I'm going to show you the exact examiner clue about gravitational fields that flips the mark scheme completely on its head. But first, you need the formula framework that makes that specific clue totally obvious to you. And the whole thing starts with W equals mg.
Before we do any calculations, we absolutely have to respect the units. Weight is a force, right? So it has to be measured in newtons. If you were doing an experiment in the lab, you'd use a spring balance to measure this, where the physical pull of gravity literally stretches the spring. You do not use a standard balance scale for weight, that's for mass. For weight, you need a mechanism that specifically reacts to pulling forces.
Let's test this out practically. On most of the Earth's surface, a 1-kilogram mass has a weight of 9.8 newtons, but Cambridge often kindly lets you round that to 10 newtons for quick calculations. You need to lock these conversions into your brain. A 1-kilo mass is a 10-newton weight. A 100-gram mass, well, remember to convert that to 0.1 kilos first, which gives you a 1-newton weight. 5 kilos gives you 50 newtons, and 50 grams gives you 0.5 newtons. Easy, right?
Spot the student error.
Okay, the stakes are rising here. I want you to look at a genuinely flawed student answer. Weight is gravity. G is how fast it falls. Ouch! Writing this loses all your method marks for vague, non-scientific wording. Now contrast this with the true top-band answer. Weight is the result of a gravitational field acting on a mass. G equals W divided by M. Boom! That is exactly what the Cambridge mark scheme demands.
Gravitational fields perfected.
So the really crucial point here is understanding exactly what the mark scheme means when it says gravitational field. Think of gravity as an invisible, action at a distance force. It can act right through the vacuum of empty space without any physical contact at all. It's exactly like the magnetic forces you feel between two magnets or electric forces between charges. It creates this invisible field of influence.
When a mass sits anywhere inside this invisible area of influence,
it experiences a force. It is in a gravitational field. And this leads us straight to a key definition you have to know. Gravitational field strength is the force acting per unit mass. Let me say that one more time so it sticks. Force per unit mass.
Now, what's really fascinating here is seeing where the formula actually comes from. It isn't just made up out of thin air. W equals mg is actually a brilliant little adaptation of Newton's second law, F equals ma. Watch this. We take force, F, and replace it with weight, W. Then we take that generic acceleration, A, and replace it with the acceleration of free fall, or gravity, G. And just like that, the result is W equals mg.
And this brilliantly illustrates how the math actually proves our physical definition. By just rearranging this equation into G equals W divided by M, we mathematically prove exactly what we just learned. Gravitational field strength, G, is the force, which is weight, per unit mass. It is a perfectly closed, beautiful logical loop.
The binge loop next step.
Okay, you now have the exact data detective framework for mass, weight, and gravitational fields. But we have a massive unresolved problem. Knowing the perfect scientific reasoning means absolutely nothing if you run out of time to actually write that examiner-safe wording on the page. In the pressure cooker of the real exam hall, students who know the material inside out still drop grades just because they haven't mastered their timing.
The pattern library continues in the next part of this explainer series, which is your absolute, mandatory next step to learn the timed answer writing system required for full marks. You've got the knowledge locked in, now you need the execution strategy.
Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE to excel in your Cambridge examinations, and jump straight into the next explainer to secure your timing strategy right now. Because, ask yourself, are you really going to let the ticking clock steal your perfect grade, or are you going to master the timing to secure the exact marks you deserve? See you there.